live in a world surrounded by technology. Yet we rarely ponder the science that lies behind the gadgets we use in our daily life. The root of many of our modern technologies lies in discoveries made by a single person who 100 years ago completely changed our ideas about science and the universe. It all started 100 years ago. The year was 1905. A 26-year-old German patents examiner named Albert Einstein, working in the Swiss Patent Office in Bern, did something that revolutionized the world of science. In a sudden outburst of genius, he turned the scientific world upside down. In the course of a single year, he produced a series of 4 classic papers, now considered to be amongst the most significant in 20th century physics, and perhaps in all the recorded history of science. Einstein's papers revolutionized the way scientists looked at the nature of space, time, and matter. Einstein was born on the 14th of March 1879 in the German town of Ulm. His father was Hermann and mother Pauline. A year after his birth, the family moved to Munich, where Einstein attended school. But he found the rigid discipline at the school intimidating and boring, and showed little scholastic ability. Because of poor grades in history, geography, and languages, Einstein had to leave school in 1894, only to resume his education later in Switzerland. His uncle aroused his interest in mathematics, and this had a lasting influence on him. After the family moved to Italy, Einstein stayed back in Switzerland to complete his schooling in Aarau. In 1896, he entered the Swiss Federal Polytechnic School in Zurich and graduated with physics and mathematics in 1900. Einstein received a PhD degree from the University of Zurich in 1905. After searching in vain for an academic position, he finally took a post with the Patent Office in Bern. At the Patent Office, Einstein's job left him with ample time to contemplate the fundamental problems in physics, and he made the most of it. In the year 1905, he published 4 of his path-breaking papers. In a symbolic fashion, these papers charted the 3 main directions in physics to which Einstein contributed the most: the theory of relativity, statistical mechanics, and the quantum theory of radiation. In the first of 3 seminal papers, which he wrote in March 1905, Einstein described how light could behave, not only like a wave, but also like a stream of particles called quanta or photons. This wave-particle duality became the foundation of what is known as quantum physics. It also provided theoretical underpinnings for such 20th century advances as television, lasers, and semiconductors. Einstein's work primarily concerned a theory propounded by the German physicist Max Planck in 1900, according to which all electromagnetic radiation, including light, is emitted as tiny packets of energy called quanta. But no one could prove that this was indeed so, because light was known to behave as waves. But there was one phenomenon that could not be explained if light behaved as waves, and that was the photoelectric effect. The phenomenon widely used today in television and digital cameras, exposure meters, solar cells, burglar alarms, photocopiers, automatic door openers, and a host of light-operated systems. The photoelectric effect was first discovered in 1887 by a German physicist, Heinrich Rudolf Hertz. Later experiments by the Austrian physicist Philipp Lenard showed that the emission of electrons depended on the color of the light. But he was unable to explain why this was so. When light is shone on a metal plate, two things can happen. Either electrons are given off, or electrons are not given off. Here we can see that when light of red or yellow color is shone on the metal plate at the right, no electrons are released, and the meter shows a 0 reading. But if blue light is shone, copious amounts of electrons are given off, and the meter shows a flow of current. Here, blue light has a higher frequency and energy than red or yellow light, and so can knock electrons off from the metal plate. If we consider light as waves, this phenomenon cannot be explained. In 1905, Einstein gave a very simple interpretation of these observations. He showed that the emission of electrons could be explained if light was considered as a stream of individual quanta or particles penetrating the metal and knocking electrons loose from atoms. In one stroke, Einstein demonstrated that light is a stream of particles. His theory could satisfactorily explain all the known properties of the photoelectric effect, and was the first result derived from the quantum theory of the interaction between radiation and matter. Einstein was awarded the 1921 Nobel Prize for Physics for this work. Einstein wrote his second paper in May 1905. It confirmed the existence of molecules and atoms by statistically showing how their random collisions explained the jerky motion of tiny particles in water, a phenomenon known as Brownian motion, because it was first observed by a Scottish botanist named Robert Brown. Before Einstein, scientists had no idea what pushed the tiny particles around. Einstein presented a mathematical theory of Brownian motion in a paper explaining the random motion to be due to the constant bombardment of the suspended particles from all sides by atoms and molecules of the liquid or gas, as we see here. A dust particle, shown as the red circle, moves randomly as it is hit by gas molecules, represented by the black dots. In a way, Einstein's theory demonstrated the existence of atoms and molecules as actual physical entities, which was experimentally proved later by a French physicist named Jean Perrin. The third of Einstein's 1905 papers was the most radical of the lot. It completely changed the way we look at simple properties such as space, time, matter, energy, and light in certain specific relativistic situations. In the simplest terms, Einstein's theory of relativity says that everything in this universe is relative. There is nothing absolute. Let's look at a very familiar experience. Suppose we are sitting in a stationary train, and the train in the adjacent track starts moving. Looking out of the window, it appears to us that it is our train that is moving, while for the passengers in the other train, our train appears to be in motion relative to theirs. But if both trains were moving in the same direction with the same velocity, then both would appear stationary relative to the other, as in this film. So, the perception of movement is relative. It depends on from where we are looking at a moving object. But there is much more to Einstein's special theory of relativity. Although in most cases velocity is relative, this does not hold true for the velocity of light, which is taken as a constant. No matter how fast one were moving toward or away from a source of light, the speed of that light beam would appear the same, a constant 300,000 kilometers per second, as we see here. When a stone is thrown with a velocity of 100 kilometers per hour from a stationary car, the measured velocity of the stone will be 100 kilometers per hour. But if the stone is thrown with a velocity of 100 kilometers per hour from a car moving at 100 kilometers per hour, its measured velocity will be 100 plus 100, that is 200 kilometers per hour. But if we shine a beam of light from the car, whether stationary or moving, its measured velocity will always be the same, 300,000 kilometers per second. But how's that possible? If the speed of light stays the same, then what's going on? Einstein provided the answer. He thought something else had to change. And that something was time. Although it may appear odd, according to Einstein, time as we measure it is not constant. It slows down at high speed. The faster we go, the more time slows down. We can say moving clocks run slow, as we see here, and it's not just theory. It has been proved by experiment. Atomic clocks carried on supersonic aircraft making long flights across the Pacific have actually been observed to slow down by a few millionths of a second compared to atomic clocks on the ground, and the difference is in exact agreement with what special relativity says it should be. Russian cosmonauts who spent a year or more in Earth orbit on the space station Mir also found their watches going slow. After orbiting in their space station at about 28,000 kilometers per hour for a year, the cosmonauts' watches fell 3.8 seconds behind Earthbound timepieces. For satellite-based services such as GPS, which rely on fast-moving satellites in orbit, accurate time measurement is of crucial importance. But clocks on fast-moving satellites run slow and, unless corrected, they can jeopardize such services. Einstein's special relativity enables scientists to compensate for time differences between stationary clocks and clocks on board orbiting spacecraft, making reliable satellite-based services possible. Special relativity brings in other strange things too. According to the theory, the length and mass of any object depends on its relative velocity. In Einstein's world, objects get shorter in the direction of motion as they approach the speed of light. So much so that at the speed of light, the length of a meter stick would appear to a stationary observer to have shrunk to zero. Under the rules of special relativity, the mass of an object also appears to increase to a stationary observer as the speed of the object increases. At 90% of the speed of light, the mass will approximately double. But at 99% of the speed of light, the mass will increase by about 7-fold. As we get closer to the speed of light, the mass increases very dramatically, until, at the speed of light, it would be infinite. To move something of infinite mass would require infinite energy, and this is clearly not possible. Hence, nothing can travel faster than light, which is also one of the implications of special relativity. In the last paper of 1905, which he wrote in September, Einstein came out with the most celebrated equation in all of science, which expresses the relationship between energy and mass, linked by the speed of light. Einstein went on to show that energy and matter were merely different faces of the same thing, their relationship described by the most famous equation in all of physics. Energy equals mass multiplied by the speed of light squared. The equation showed that very small amounts of mass might be converted into a very large amount of energy. In a nuclear chain reaction, when atoms of a heavy element like uranium split into two, some mass goes missing and appears as energy. When the process occurs very fast, huge amounts of energy are released, as happens in an atom bomb. Einstein was aware that an understanding of this formula could lead to the most destructive weapon, although peaceful by nature and politics. In 1939, he helped write a letter to the President of the United States, urging him to fund research for the development of an atomic bomb before the Nazis or Japan developed their own first. The result was the Manhattan Project, which produced the atomic bomb dropped on the Japanese city of Hiroshima, which killed 80,000 people and maimed more than 60,000.
Verehrte An- und Abwesende, wenn ihr den Rundfunk höret.
Einstein was shocked by the devastation and loss of life. He lamented, "If only I had known, I should have become a watchmaker." On the brighter side, Einstein's special relativity has enabled us to understand the stupendous source of the energy produced in the sun and in the stars. It has also enabled us to harness the power of the atom in nuclear reactors for peaceful purposes. Although the year 1905 was the high water mark of Einstein's scientific genius, his output did not flounder. In 1907, 2 years after proposing the special theory of relativity, Einstein wondered how Newtonian gravitation would have to be modified to fit in with special relativity. And then came his crowning glory, perhaps the most beautiful theory in all of science, the general theory of relativity, published in 1915. Like the special theory, it was also based on a thought experiment. Why do we feel weightless when we fall? As any diver at the swimming pool would know.
Start well. Not perfect synchro, but almost.
For any object falling under gravity, the weight becomes zero, as we can see here. Astronauts in a spacecraft float around for the same reason. Einstein equated the experience of free fall in a gravitational field and that of floating in a gravity-free region of space, which he said were indistinguishable from each other. The man here feels a downward pull due to Earth's gravity. Here also the man feels a downward pull, but due to the upward acceleration of the rocket. But we can't distinguish one from the other. That is, we can't tell gravity from acceleration. This interpretation formed the basis of what Einstein called the equivalence principle, which describes gravitation and acceleration as different perspectives of the same thing. By equating gravity with acceleration, Einstein changed the very concept of gravity. According to him, planets moved around the sun not because of gravitational pull, but because the sun has warped the space around it. The planets only follow the curved space-time. By 1911, Einstein was able to make preliminary predictions about how a ray of light from a distant star passing near the sun would appear to be attracted or bent slightly in the direction of the sun's mass by following the space-time curvature. Einstein's prediction about the bending of starlight was dramatically proved during a total eclipse of the sun in 1919, when a star which ought to have been hidden behind the sun appeared visible in photographs taken during totality. In 1917, Einstein came out with yet another paper, introducing the idea of stimulated emission of radiation. Light sources such as candles, fluorescent tubes, and light bulbs give off light when atoms in their gas or filament are excited by energy. But these sources give off light in every direction in a chaotic manner. Einstein suggested that atoms could also be artificially stimulated to emit photons. This stimulated emission of light would produce a highly concentrated, bright and powerful beam of light of a single color. This light would be emitted in a single direction and could be used in many applications. Although Einstein did not invent the laser, his work laid the foundation. In 1924, Einstein received a paper from the Indian physicist Satyendranath Bose that described light as a gas consisting of photons. Bose had described this photon gas as a strange type of gas, for the particles in it did not obey the common-sense statistical laws. This led to the formulation of the famous Bose-Einstein statistics and the concept of particles called bosons, several of which have been detected experimentally in particle accelerators. The two scientists also predicted a new state of matter called Bose-Einstein condensate, which has already been achieved. Textbooks sometimes state that Einstein's theories do not affect our everyday life because we never travel anywhere close to the speed of light. But, as we have seen, Einstein's theories affect us all. In fact, the very existence of life on Earth is because of relativity that governs the production of energy in the sun. We use hundreds of gadgets that are based on Einstein's work. How could one man achieve so much? It was Einstein's genius that made it possible. Einstein was a daring, wildly ingenious, and passionately curious person. He saw the universe as a puzzle, and he delighted in trying to solve its mysteries. All he needed to contemplate the cosmos was his most valuable scientific tool, his imagination. He reinterpreted the inner workings of nature, the very essence of light, time, energy, and gravity. As we have seen, his 4 classic papers of 1905 fundamentally changed physics, the way we look at the universe, and made him the most famous scientist of the 20th century. And it all started 100 years ago, in that eventful year which historians have called Einstein's miraculous year.